right, so over the last month, we've focused on a couple different things that are all going to come together today and throughout the rest of this week. We've looked a lot at polynomials, right, which are just multi-termed expressions, usually more than 3 terms we refer to as polynomial. And we've also looked at factoring quadratic expressions a lot and using those factored forms to solve equations. So what we're going to do is start looking at how to factor higher term polynomials, right? More than just quadratics. Today we're going to start by looking at cubic polynomials. So that just means that the highest degree is 3, right? That's what cubic means. And let's kind of come up with a strategy for doing that. We're going to factor out a GCF if there is one. We're not really going to focus on that today just because of the nature of how we're kind of doing school right now. But know that that should always be a first step, is look for a greatest common factor and factor that out. Another thing we're not going to focus too much on right now, but that you should keep in mind is that we should always make sure things are in standard form. So if this is not in standard form, if your expression is not in standard form, just rearrange it so that we have the exponents going down 3, 2, 1, 0. So where we're really going to begin is factoring by grouping, which is something that we already know exactly how to do. Split up the 4-term expression into 2 separate 2-term expressions, factor a GCF from each. We should have an identical factor resulting, and we factor that out. We used exactly this strategy when we factored quadratics, which should make this pretty simple. The only difference, which is a nice, easy difference, is that factoring cubic expressions doesn't require us to split the middle, right? So when we looked at quadratics, we had to split the middle and then factor by grouping, but now we don't need to do that because we already have 4 terms. So an expression is factored completely when you can no longer factor. For today's purposes, the only thing we're going to really have to worry about there is paying attention to when we can use a difference of squares, right? We want to break this down as much as possible. And usually when we're factoring by grouping, that's all we can do is we factor by grouping and we get 2 factors and we're done. But sometimes one of those resulting factors is a difference of squares and we can factor it even further. And we'll see one example of that in here. So let's just go through our process that we already know of factoring by grouping. So I'm going to split this up into the first 2 terms and the second 2 terms. From the first 2 terms, I'm going to look for what these have in common. I'm going to look at the coefficients, which are 1 and 2. They don't have anything in common except a 1, so we're not going to factor that out. And the x cubed and x squared, what these have in common is a factor of x squared. We always just kind of look at the lowest exponent on x for that. So I can divide both of these by x squared. Over here, we're going to do the same thing. So remember that this sign always comes down. So when we're factoring by grouping, that negative sign means we should factor a negative out. And we're going to look at the coefficients, 8 and 16. These have a factor of 8 in common. And then we're going to look at the variables, x, and since this is constant, there's no x, we can't factor an x out. So let's actually factor those GCFs out. We pull out an x squared from here, and then divide x to the 3rd divided by x to the 2nd gives us x to the 1st, or just x, right? Those are our exponent rules coming back into play. Over here, dividing 2x squared by x squared, these cancel out and just leave us with 2, positive 2. So we get x squared times x plus 2. Then in the next 2 terms, we're factoring out minus 8 and dividing everything by negative 8, right? Negative 8x divided by negative 8 gives us positive x, and negative 16 divided by negative 8 gives us positive 2. So this is where we pay attention and make sure that the x plus 2's match each other perfectly. And it's only because they do match that we can factor the x plus 2 out and be left with x squared minus 8. So this is our final factored expression. The only other thing we'd want to do, like I said, is make sure it's factored completely by checking if this is a difference of squares. So x plus 2 is what it is, and that's usually done because it's a linear expression. This x squared minus 8, sometimes we can factor more. For example, you should remember from last week we talked about difference of squares. Something like x squared minus 9 can be factored to x minus 3, x plus 3. This one can't be broken down anymore because this 8 is not a perfect square. But if that 8 is a perfect square, we're going to want to pay attention and continue factoring even more. And we'll see how to do that when we get there. In our next example, same thing, right? We're going to look at the first two terms separate from the next two terms. Between 6 and 9, I have a common factor of 3. And I'm always going to be able to factor out an x squared here because the lowest exponent is 2. I'm going to make sure I factor out this negative sign. So negative, right, 14 and 21, these have 7 in common, and there are no x's in common because there are no x's on the 21. So let's divide those out, or factor those out, I should say. So we factor out a 3x squared. 6 divided by 3 gives me 2. X cubed divided by x squared gives me x. 9 divided by 3 gives me 3, and x squared divided by x squared cancels, so I'm left with 2x plus 3. In the next two terms, I'm going to factor out a minus 7, and then we divide. Negative 14x divided by negative 7 is 2x. Negative 21 divided by negative 7 is positive 3. We check to make sure that these are exactly the same, 2x plus 3 and 2x plus 3. That allows us to factor it out and be left with 3x squared minus 7. And again, for today, the only thing to look for from here is, can we break down the quadratic factor even more by using difference of squares? But again, we can't here because this is not a perfect square. Some more examples of the same thing. First two terms separate from the second two terms. The first two terms have a factor of x squared in common, right? This is a coefficient of 1 and negative 4, so there's no coefficient attached. And we can always factor out an x squared from the first two terms because of this x squared here. Here, I'm going to factor out this negative sign, so negative. And I'm going to look at, what do 9 and 36 have in common? Those have a factor of 9 in common. 9 goes into both of those. And I can't factor out any x's because there are no x's here. So when we factor out the x squared, we divide it out. X to the third divided by x to the second gives us x. Negative 4x squared divided by x squared. These cancel and just give us minus 4. Over here, we are factoring out the minus 9. So negative 9x divided by negative 9 gives us just x. And 36 divided by negative 9 gives us negative 4. So we double check our work now by seeing that x minus 4 matches exactly with x minus 4 here, meaning we can factor it out and be left with x squared minus 9. So I've been mentioning in every problem that we should check if this is a difference of squares. And in this case, it actually is a difference of squares. So the x minus 4, I told you, just is what it is. That has to stay because it's already linear, meaning it's broken down as much as it can be. The x squared minus 9, we should remember from last week how to factor a difference of squares, is x, right? We're thinking about the square root of 9. And this breaks into x minus 3, x plus 3, because the square root of 9 is 3. And so because this is cubic, it breaks down and gives us 3 solutions. And in this case, we can find those solutions actually by just factoring it into 3 factors, 3 linear factors, x minus 4 times x minus 3 times x plus 3. And if we multiplied these all back out, we would get this expression. So let's look at one more. From the first two terms, The coefficients 4 and 1 don't have anything in common, but I can always factor out an x squared. The coefficients 100 and 25 have a factor of 25 in common, and I can't factor out any x's because there are no x's here. So we get x squared dividing 4x to the third divided by x squared gives us 4x, and x squared divided by x squared is just 1. Then we're factoring out the 25. 100x divided by 25 gives us 4x. 25 divided by 25 gives us 1. Because these match exactly 4x plus 1 and 4x plus 1, we can factor it out, and we're left with x squared plus 25. So we're always going to check, can we factor the quadratic term even more? The quadratic expression, I should say, even more. This almost looks like we can because 25 is a perfect square, but remember that is only a difference of squares. So if this were subtraction, we could factor more, but because it's addition, we're done factoring. We would have to start using complex numbers if we wanted to break this down even more, and we are not getting into that today. So this is our final factored expression, and that's how you factor by grouping. Go back and rewatch any examples if you need. Make sure you pay attention to examples like this. Continue to factor even more if you can use a difference of squares.